Krishna. Welcome back to the Atma Paradigm, and we're in part 4 of our series, which is the universe and beyond. Last week, we offered a synopsis of the key points established within the first parts 1, 2, and 3 of our series, and these key points included that any explanation of the universe and reality must account for us in it. But we're going further than that. Through our analysis, we've come to the conclusion that consciousness is a fundamental component of reality. It's not produced from the complexity of matter or the workings of the universe or the small bit we call the brain. Consciousness is to be considered as perennial as the universe itself. So our question is, might it be a player in the unfolding of the universe? Especially as we have considered how the interaction that consciousness has with the physical stuff we call matter. So, and the ability of consciousness to impart novel, specifying information into a material or physical system. Excuse me. As we'll see today, the universe contains a lot of information, and we'll be questioning where that information comes from. A standard physicalist assumption would be to claim it's a combination of all the chance interactions of the fundamental properties of all the little bits and pieces acting under the laws of physics. But what if we see that the model of the universe is unable to explain the starting information that define those fundamental properties, or the parameters of how those forces of physics operate? And if that's the case, then it means we may be looking for a different explanation for the overabundance of information that we see in the universe. Now, fortunately, within our paradigm, we have another component to add into the mix, i.e. conscious agency, something we know to be a source and generator of useful specifying information. So will that change our calculation of what's happening in the universe and how the universe comes to embody so much information? And we'll also be looking at what that information is trying and striving to manifest, which, at least on this rocky planet we call home, is that it's trying to manifest life. Is the universe's purpose or inevitable direction then to fulfill the objectives of what we call life, to accommodate the will of consciousness for experience and activity in whatever forms and bodies the cosmos can provide? That's our rationale for approaching these major themes of science and philosophy in this order: consciousness, matter and reality, then life, and now the universe. So today we begin our look at existence in terms of the reality in which we find ourselves, this place we regard as home, a rocky planet called Earth floating in an unfathomable expanse of space. But first we give some kind of definitions for clarification. We're going to be talking about cosmology. And cosmology, interestingly, is defined as both a philosophical and a scientific pursuit. As a philosophy, it considers the origin and structure of the universe, but particularly from the point of view of the nature of matter, space, time, information, and causality. Now, as a branch of astronomy, cosmology is also a science. It's a science also of the origin and development of the universe, but it brings together observational astronomy and particle physics. So, understanding that there are these two definitions, I think we can assume that cosmology requires to be a cooperative discourse between science and philosophy, trying to achieve consensus on what is a reasonable and reliable narrative of where we find ourselves. And cosmogony then is the specific focus of cosmology which deals with the origin of the universe. And often this word is used in regard to the theory which seeks to explain the origin and structural development of the universe. And then we have a third word, cosmography. And this is the discipline which tries to map out and provide a description or a depiction of the universe. Now, in exploring cosmology and cosmogony, my focus will be on certain philosophical principles to do with causality and information. And we'll be analysing the standard scientific evidence and theoretical narratives in light of those issues. And we'll consider the need to apply the principles that we established in the earlier talks of this series. For instance, that consciousness is a fundamental component of reality, and that matter is energy and information manifesting physical properties. And information increases complexity of physical properties and interactions. And consciousness is a source of novel, specifying information. Now, cosmogony and cosmology set out to explain the universe as it is and how it came to be that way. And so the view that I'm going to present is that cosmology, it needs to account for these three aspects of reality that we have established as extant, existing within our universe, realities, namely consciousness, information, and manifested physical reality, and to take account of the relationship that exists between all three. Now, I think many of the world's wisdom cultures intuitively incorporated these three aspects of consciousness, information, manifestation into their cosmography, their depiction of the cosmos, and also into their cosmogony, the narrative of how they believe the universe came to be. But one model of the universe hasn't tried to do that. And that one is the standard model of cosmology related to modern astrophysics. Now, modern cosmology has seen incredible advances in its observations, in its ideas, and that's largely thanks to unparalleled innovation of astronomical equipment, the building of ideas and the discoveries over centuries, and also the incredible international cooperation that has been done in major projects like CERN and LIGO. And this has led to the current understanding that is presented as the standard model of the development of the universe. Now, we mentioned in earlier talks that currently there is no standard model for what is consciousness and where it comes from, nor is there a standard model for what is life and where it comes from. In both cases of consciousness and life, the science that is used to deal with them explains the interactions of physics, chemistry, and biology, but fails to find properties and interactions in matter that it could account for these two phenomena, consciousness and life. Whereas there are standard models for both matter and for the universe. So what you can draw from that is that it's clear that the scientific method is much more comfortable when it targets inert matter stuff, either as the very small things within the subatomic scale or the very large phenomena at the scale of the cosmos. These are not easy things to investigate, but for science, they're a lot easier than the issues of consciousness and the actual nature of what makes us alive. And because the physicalist assumption is that these pesky things, life and consciousness, appear very late in the game, in the story of the universe, and perhaps they're only an incredibly lucky accident in one little corner of the cosmos that we call Earth, I think many physicalists feel that it's entirely reasonable to proceed with an explanation of the cosmos in terms of matter alone, i.e. not involving consciousness and life. But even though these standard models try to avoid consciousness and life, they still have to deal with that other member of our threesome, information. And as we're going to see today and developed through several talks, without consciousness there to help them, things can get pretty untidy, and their information itself poses a problem. Because as physicalists and physicists rather, and cosmologists discovered during the 20th century, where you have matter, you have information. And where matter has structure, you have extra information. So as we'll see in our analysis as we go along, the information bit that exists alongside with the energy aspect of matter is not being treated with the same ontogeny, the same concern for where it has come from. I'd say that physicists try to be very precise about the processes that address the energetic aspects of matter. That's what the calculations are all about. But they seem pretty cavalier when it comes for accounting for the quantity or the specifics or a source of information. The information contained within the properties of the fundamental components of matter that they're looking at, or within the laws that appear to govern those interactions of their components. And I suggest that this failing at an early stage of the model of the cosmos, i.e. the failing to include consciousness and information as kind of coexistent with matter in terms of your explanation, that failing at the beginning of the model of the universe perpetuates into the later stages. And that becomes evident when we hear the rather vague and imprecise explanations of how matter becomes structured into particular arrangements of galaxies, solar systems, and planets, etc. Now, I'm not saying there's no attempt to explain the information within properties, laws, and structures. But compared to the intricate mathematics that goes into the calculations of energy content, the accounts of where new or additional or reorganized information comes from are pretty light on detail. Now, it's true there is an adherence to the relatively recent principle that information, like energy, is conserved, at least in the quantum world. It can never be created or destroyed. But that care is not applied to explanations of increased information content of things in the classical world. You know, the big stuff, the macro stuff that we see around us, the structures of galaxies and planets and so on. Instead, the explanations of increased order in the universe are pretty thin on causality, and they often rely on what we will identify as low information processes, which often involve chance interactions or of components, or a generalized force effect such as gravitational pull. As we'll see, gravitational pull doesn't increase entropy. It simply just moves things around. Random interactions and forces like gravity pull things together, but they don't impart specific information needed for morphological structure. They don't define its form, nor can they increase order by reducing the high level of entropy. So, hence the causality of structure and increased order in the universe, I suggest, deserves much more respect and better explanations. And this is going to be a recurrent theme as we go along. I'll do my best to cover these points as clearly as I can during these talks. But it's why we have given our title for today, A Universe of Information. So we're going to begin with how the standard model depicts the universe. And I'm focusing on the standard model narrative. We are here, and when we look out from our home planet, we see the observable universe. Now, the great thing about what we call the observable universe is that by definition, you're always at the center of it. And we always want to be at the center of the universe. So the observable universe is the extent of everything that's out there that we can see from our location on planet Earth. It's the universe from our perspective. And we really only have very minor ability to adjust our viewing point of that perspective. However, in recent decades, thanks to all the instrumentation we've been talking about, scientists have been able to extend the scope of how far they can see from here. And because we rely on light or other types of waves to reach us from these far off places, we're receiving data about those places as they were millions and often billions and billions of years ago. So here it is in this picture. It's an interesting three-dimensional universe represented in a two-dimensional map, with the distances going out from the center in a logarithmic scale. So the little bits on the outside are kind of very, very far away and has shrunken very much in scale as we see this map. Now, according to the standard model, the universe, of course, doesn't really have a center. It's not like there is a point that exploded and everything is centered around that thing that went bang. No. The physicist Fred Hoyle gave the analogy of a balloon with dots and squiggles on the kind of surface of the balloon, and those squiggles represent the galaxies in space. Now, over time, you can blow up the balloon and it expands, and the dots on it are now further apart than they were. Therefore, it's like space has expanded, and the galaxies are now further away from each other, but it's space that is expanding and the galaxies remaining the same. Now, with this analogy, as with any of the analogies we use today and in talks, they all just apply to the point that they are making, you know, in a particular context. It's very hard to mix these kind of analogies up with one another. But in this analogy, important things to note. One is that the three-dimensional universe is being represented on a two-dimensional surface, just to help us get our head around the concept. So whatever is space, you know, that's the balloon surface. And there is no extra dimensional space outside of the balloon. The surface of the balloon is all that there is. All that exists is the ever-stretching skin of the balloon. But this idea of an expanding universe in Western astronomy is actually quite a new idea. It's barely 100 years old. And in order to prepare us for examining the ideas of the Standard Model, I thought it'd be useful if we kind of go through part of the history of how and why the scientists develop the Standard Model as it is understood now. At the end of the 19th century, basically European scientists thought that all that there was of the universe, or that the universe was just as big as the Milky Way, that was it. And they also thought that the universe itself was static, because everything looked reliably immovable and permanent out there. But all this changed, of course, with the new physics of the early 20th century. Einstein had developed a set of equations. Here he is, Albert Einstein with Willem de Sitter. And Einstein had developed his set of equations that could describe the general configuration of matter and space, taking the universe as a whole. And these were recognized as being really, really useful as a foundation on which to build a kind of science of cosmology. The trouble was that finding a solution to his equations that would produce a model of the universe was actually a mathematical nightmare. So Einstein met with Willem de Sitter and they discussed it. They had different ideas, and each of them managed to work out their own solution to Einstein's equations. However, both solutions weren't quite right and needed adjustments in order to be able to describe a stable, static universe. That's what they were trying to do. That's what they understood the situation was. Einstein stabilized his solution by adding the hypothetical term called a cosmological constant. It's just a figure he put in there so that it kind of worked, and it kind of gave his equations a sort of, his solutions, a kind of quasi-static distribution of matter. Now, this was all very theoretical. But then came along some observational evidence. The founder of the Lovell Observatory in Arizona was Percival Lovell. And he set a task for his assistant, Vesto Slipher. And he told him to study the spectra, the light coming from nearby nebulae. Now, nebulae, like the Andromeda one that Slipher studied, are clouds of gases and dust. But they're kind of, you see them up in the sky and they're kind of just this nebulous area, hence the name. So what Slipher found was that when he looked at this Andromeda nebula, he found it was hurtling towards us very, very fast. And he thought, that's weird, because we thought the things out there in space were meant to be kind of permanent fixtures and not meant to be moving like this. So he thought, better have a look at some of the other nebulae. And at first, he thought he was noticing a pattern. He thought that he could find nebulae that were approaching Earth on the south side of the sky, but when he looked at the north side, the nebulae seemed to be receding. So in that case, he thought, well, maybe they're fixed, but it's us, our Milky Way galaxy. Maybe that's what's drifting, from the north to the south, or going towards, from the south rather, to the north, towards Andromeda, and away from the others on the south side. But he kept up his measurements, and he realized, no, he hadn't got it right. Really, there was only 3 out of all his measurements that seemed to be approaching. All the other nebulae in all directions were receding. So this kind of made him change his mind on this, and he began to think, well, in that case, if everything is receding away from me in whatever direction I look at, then this indicates maybe the universe isn't static, maybe it's expanding. So he discussed these ideas with Edwin Hubble, who worked at the Mount Wilson Observatory. And Hubble and his team began a study of distant faint nebula. So these are ones that don't give off a huge amount of light. But with these faint nebulae, he was able to work out not only the movement and velocities of the nebula, which direction they were moving and how fast, but also he understood their distances from Earth. And he then presented the graph that is shown. That's his original kind of hand-drawn graph from 1929. And he presented this graph, which basically ruled out Einstein's commitment to a static university and indicated that De Sitter, who had started exploring the idea of an expanding universe, might be correct. Now, interestingly, once the presumption that the scientists had been cleared out of the way, i.e. when they got rid of this idea that Einstein's equations had to satisfy a static universe, once they got rid of that, then everyone was able to look at his equations completely afresh. So this is a nice example of how sometimes there can be a presumption about how things must be interpreted, what they've got to show. And you get into trouble or you get into a dead end that way, and you need to step back and a new idea is required. So once static universe was out of the picture, the other scientists were looking afresh at Einstein's equations and actually were starting to produce solutions that were variations of their own expanding universe ideas. But the person who history seems to favor in this regard is Georges Lemaitre, who was a Jesuit Catholic priest. Now, one of the reasons why he is picked out as and given special preference in this is because he had already submitted a paper about his idea of an expanding universe before the Hubble evidence came out. So when he found out that Hubble had produced this graph and were showing that there seems to be evidence of an expanding universe, he wrote to his own mentor, who was Arthur Eddington, who had previously helped Einstein. And Arthur Eddington, he told Arthur, look, you remember the paper I wrote that everyone ignored a few years back? Eddington went back to the paper, read it, got excited, and he referred it to Einstein. Einstein then said, yeah, actually, this paper works. I mean, his model actually is consistent with general relativity, So that got the thumbs up. De Sitter also then started to praise Lemaitre and gave him the credit for the brilliant discovery of the expanding universe. And Lemaitre then went on to develop what was sometimes called the fireworks theory, which is very appropriate for tonight, 5th of November here in the UK. We have fireworks night, so if you hear things going off in the background in a bit, then that's another universe being formed. Anyway, the fireworks theory of Lemaitre was that there is a primeval cosmic egg which explodes. And the universe we see now, he called the remnants of ashes and smoke left over from this bright but very rapid fireworks. And this was the inception of Big Bang Theory. And actually, probably the conception of this idea of an actual explosion of stuff is still what people think of in terms of the Big Bang idea. However, the new idea, this new idea that the universe had been expanding for eons, of course raised some questions. And the most important one was, well, if it's not static and we just thought it'd been there forever, and it's expanding, well, kind of then, you know, it's big and then it must have gone small. It must not, you know, must have been very, very small, way, way back. Does the universe therefore have a beginning? Now, this was a novel idea, that which is the universe, there might have been a period when it did not exist. It was a novel idea for Western cosmology, because up to then it was eternal, it's always been there, much the same way. So this was a new thing. Well, in that case, what can we say about this beginning? So there were things to be decided. And here you see George Gamow, another physicist, and this is a kind of picture that was created way back. It shows him appearing as a genie out of a bottle, and the bottle is called Elam, or Ilam, which is an old medieval term for creation, pretty well out of nothing. And Ilam has also now become to refer the hypothetical plasma stuff that exists in the first moments of the universe before physical elements and i.e., atoms, etc., were formed. So anyway, Gamow suggested that the universe started with a state of infinite density, i.e., that means there's infinite mass, the whole mass of the universe, that everything that's out there, but in an infinitesimal volume. So all the mass we could possibly think of in the smallest volume that could ever exist, and it existed in that state at an infinite temperature. And then, after it appeared, then it started to cool, and as it cooled, maybe from then the simplest chemicals, hydrogen and helium, could be produced, or at least initially they would have their nucleus, their nucleons appear, and as the temperature then further dropped, these nucleons could combine with an electron and form hydrogen, and then you can get helium from hydrogen. So, but he couldn't find any elements heavier than helium from this process, and it was later on that Fred Hoyle showed how the other elements, at least up to iron, could be produced in the fusion processes within stars. So this idea explained, and see Hoyle's explanation of the elements, he thought it was rather good because it explained the elements without recourse to the idea of an expanding universe. And he didn't really like the idea of Big Bang and the expanding universe because he had his own idea, which was called steady state. And this led to what's probably the biggest debate in 20th century cosmology: Big Bang or Fred Hoyle's steady state. Now, in the 1950s is when this really kind of kicked off. Gamow was in direct argument with Hoyle over their competing theories. And it was Hoyle who coined the phrase Big Bang, and he meant that as a derogatory term for what he considered, and I quote, an irrational process that cannot be described in scientific terms nor challenged by an appeal to observation. I.e., you can never see the beginning of the universe, and therefore you will never observe it at that point. Hoyle preferred his own steady state theory, which suggested that the universe was unchanging, but at the same time, in some way, dynamic. Now, Hoyle is also responsible for another key tenet of cosmological thinking, which is called the perfect cosmological principle. And that the idea is that the known universe is the same at any place and at any time. It is homogeneous, like homogenized milk. It's the same mixture of stuff everywhere. And it is isotropic, which means that it has a physical property that has the same value when measured in different directions. For instance, glass is isotropic. You cut it this way and cut it that way, it'll still look the same when you look at it at its kind of granular or structure. Whereas wood is anisotropic because it has grain running in one direction, and when you look at the other way, you have to cross the grain. So this idea of Hoyle, that there is this kind of perfect cosmological principle of the universe being the same everywhere, was actually an updating of Copernicus. And it really was aimed at setting the scene that humans and Earth have no real special place in the universe. We're just in one lonely spot in a vast, centerless universe. Now, observations since Hoyle's time have broadly supported an isotropic universe, and we're going to talk about some aspects of that. There are important variations within that isotropy, which we're going to talk on next week. And there is a very interesting anomaly referred to as the axis of evil, which we'll also come to another time. But back to the squabble of steady state and Big Bang. How are people going to decide between them? All right. So this is kind of the scorecard that I've drawn up to show you how the argument sort of went. So it's a chart of all the key issues that each theory had to deal with and the differing predictions that their theories offered. So the first one, density of the universe. What did their theories predict about the density of matter within the universe? Now, Hoyle's steady state said density would be constant over time, because he said, and there's a little diagram here, the one at the bottom is the steady state situation. Okay, the universe may be expanding, but Hoyle had the idea that as it expands, more matter appears to fill it in, so the density never changes. Whereas the Big Bang theory or evolutionary theory of the universe, which is the one at the top, shows as the universe expands, then the matter that's in it is further apart, i.e. the density has reduced. Now, at that time, there wasn't any evidence either way, so it was, and I've done the scores at the side, SS, steady state, scored 0, and Big Bang, 0, so scoreless draw on that one. And the next one, age of the universe. By definition, the steady state says that the universe is changeless and ageless, whereas Big Bang could propose an age, that you could calculate backwards and find a specific age of the universe. The only problem for the theory at that time in the 1950s was that the age it calculated was younger than astronomers at the time thought the age of the solar system. So there was no point having a theory that says the universe is younger than the solar system. So that was actually a score for steady state, 1-0. Then rate of expansion. And steady state suggested there was steady expansion, it was constant. Gamow, on behalf of Big Bang, reckoned, no, the expansion should slow down because it started very energetically, but somehow or other it's going to be losing energy over time. That expansion should slow down gradually. Now, the evidence at the time sort of favored Big Bang, but it wasn't conclusive. So later on, they found that the rate was changing, but at the time, this one, it was scoreless. So they couldn't decide between them. Then the age of galaxies. Now, this is one that they could test. Steady state had this idea that we've just talked about, that as space expands, new matter appears to fill in it, to fill the space as it's kind of growing. Now, this means that there will be new galaxies being formed all the time. And these new galaxies will be interspersed amongst the older existing ones. So, whereas steady state just said, no, galaxies age with time and there'd be no mixing of old and young. And this was something that could be observed, that galaxies, when they were observed the further away, and therefore the older they were in their distant past, were seen to be younger. And there was no observed mixing of older and younger galaxies. So score for Big Bang on this one. Now, this is the next one's very interesting. The background microwave radiation. Steady state proposed that after the universe, the Big Bang proposed that just after the universe started, there would be hot plasma which would cool as space expanded. And that at a certain cooler temperature, there would be a process which I'm going to talk about a little bit later, called recombination, which was the point where electrons and nucleons came together to form actual atoms. And this released lots of photons as light energy, and that has produced what is assumed to be the background microwave radiation. And where a steady state said there shouldn't be any of that, the Big Bang theory said, yeah, there could be a microwave background microwave radiation, and they did even some calculations on it. And at the time, they worked out that their idea of the expansion and what the temperatures might have been and how that might have been affected by the size of the universe, they reckoned that the universe out there and the coldness of space was actually 5 degrees Kelvin. That's just 5 degrees Celsius above absolute zero. And at that time, it wasn't possible to measure that sort of level of radiation. So it was still nil all at that time. The game was evenly drawn. So things became really heated and political and ideological. Scientists split into different camps, and the preferences weren't always rational. Steady state was labeled as a kind of communist or some kind of anarchistic theory, which really wasn't fair. And Pope Pius XII, the Pope at the time, weighed in favor of Big Bang. Partly maybe because Lemaitre was himself a Jewish Catholic priest, but also because Pope Pius thought, well, a universe that has an actual starting point probably is in more keeping with our biblical idea of creation. Anyway, the debate went on, but two things happened that changed the weighting of the scores. And the first was that there was revised calculations for the Big Bang's age of the universe. Instead of calculating that the universe must be younger than the solar system, they realized that we're out by a factor of 2 or so. So that gave an age of the universe, according to Big Bang, at around 10 billion years or so. Much more acceptable. So wasn't a proof in itself, but at least it nullified the goal against it. So the age of the universe, where there was 1 under steady state, there's now 0. That score was cancelled. But the evidence that settled the matter for most astronomers, and it will be how it is discussed in all the textbooks, came from newfangled technology, radio astronomy. And in 1963, 2 astronomers, shown here, Robert Wilson and Arno Penzias, were working for Bell Telephone Laboratories. And they were studying the sky's microwave noise. And they discovered they were receiving microwaves from all around the sky, a kind of universal background radiation. And at first they thought they were a mistake, and the story is they went and cleaned out the dish again and again. They set up pigeon traps because they thought maybe it's just birds evacuating on their dish. So they tried all these things to see if they could remove this weird little signal they were getting. But no, it persisted. And they realized we are getting a single reading. It's a wavelength of about 1 millimeter, and it's coming from everywhere in the sky. It's pervasive. It's not from a particular object out there. It's just background radiation. So Robert Dick at Princeton kind of latched onto it, and he calculated that this wavelength suggested that the temperature of the cosmos out there was radiating at about 3 degrees Kelvin in all directions. Now, that wasn't necessarily conclusive for a number of issues, but it was seized upon as a big score for Big Bang. They had thought 5 Kelvin as a prediction, and if Robert Dick reckons it's 3 Kelvin, that's pretty good. So that was the score for Big Bang and why it has become the reigning theory. However, as a theory, it was still in its infancy. It needed help to develop into what is now the standard theory of cosmology. And this picture of the cosmic microwave background radiation, which you see here, it clinched the success with the Big Bang, but it had its own, there was a big question on it. And that was, which I'll explain here. But first, let me explain why this map is shown in a kind of oval-shaped way. It's representing the whole universe, but in the same way that a globe of the Earth is kind of projected onto a 2D piece of paper, as it's shown there. So this kind of globe of the universe, which, and this is back to the balloon idea, is now being mapped in terms of this oval-shaped universe. It's giving us an idea of what's out there. And it's not trying to place things in a specific location or the size. But what it does tell us is something very interesting, which we'll come to. Now, the map shows the radiation that we see from the sky in all directions. It's radiation that was released from an event that's said to happen about 380,000 years after the Big Bang. Here's its history. During the first 380,000 years or so, timings vary, matter existed as hot plasma. It was a sea of baryons, which are the things that make up the nucleus of atoms, say, but without actually being atoms. So a nucleon, like you'd find inside hydrogen thing, which is basically a proton without an electron. So this plasma was just too hot to form actual atoms of hydrogen or later helium. But there were lots and lots of photons, those particles of light present. And they spent their time bouncing around off the baryons and the electrons. And as they were bouncing around, they couldn't go anywhere. They just kept, wherever you go, it's just like being in a big crowd. You just bumped into something. They were losing energy. They couldn't escape. They couldn't go anywhere. So in effect, space was opaque. Light could not pass through it. Then around the 380,000 year mark, the plasma had cooled sufficiently for the electrons and the baryons to combine to form atoms. And this stage is called recombination. It's a little misleading because the atoms had never been combined previously. So it was really combination rather than recombination. But now that the plasma sea had been tamed, the plasma sea, there was a seething mass of baryons and electrons causing problems for the photons, it had been tamed into a more open state, kind of gaseous state of real atoms. Then you can see the little kind of horizontal lines. These were the photons. They are now being liberated. They were free to move about, and from this time on, space was transparent. So from the subsequent effect of the recombination gives another effect where the electrons first arrive at a higher kind of energy state and then drop down to their ground state within the atom. And as they do that, more photons are produced. So that's called decoupling, where photons are actually decoupling from the formation of the atoms. So it's adding to the light of the universe. Now, sometimes you hear of the cosmic microwave background being called the afterglow of the Big Bang, as if it was the kind of leftover fire light of a big fiery explosion. And that doesn't give you a true impression. However, essentially, as far as the standard model is concerned, this release of photons creates the first thing and the oldest thing that can be observed. So it is as far back as we can ever go in directly observing the early universe. We are not able to see beyond that point of 380,000 years, which is actually quite late in the process, as we'll come to. Nothing earlier can be ascertained by observation of any type of radiation. So if we want to come to an understanding of what happens before that, we have to use inference and conjecture. to propose what happened before this point. Now, obviously, that has to be done intelligently with calculations, with theories, and what it has to try and do, of course, is explain what at least we do see at 380,000 years. And that was what was being trying to do here, that if this is the oldest release or freeing of photons, if this gives rise to the cosmic microwave background, well, then we're kind of looking at it in the world there, and the idea is that the simplicity and the pervasiveness of this radiation comes to us from a time before any of the actual structures of galaxies and planets complicated the universe. Now, the big question for the CMB map, as we see it here, is that it seems that the radiation from all parts of the universe is remarkably similar in temperature. Now, you've got to remember that the colors you see here are kind of Photoshop additions. They just show the variations of radiation levels that were received, but it's not that the universe was this color or anything. And it does look like there is some variation, but actually you'll see that that variation is tiny, really, really tiny. In fact, the actual variance at large scales is small, and what you're actually seeing from any one place to another has a variance, and the actual temperature is just under 3, which is 2.726 Kelvin, and it varies across the sky at 0.001. So instead of 2726, it could be 2727 or 2.725. So a very small difference. And that raised a big question. How come? And it's sometimes called the horizon problem, or the homogeneity problem. We talked about homogeneous, like your bottle of milk. When milk comes out of the cow and sits for a bit, the cream separates. That's what normally happens. However, modern consumers don't like that, the cream with their milk, as we used to have when I was a kid. So the standard practice for dairies is to homogenize the milk by shaking it, and the fatty cream then kind of fatty cream globules then break down and merge in with the milk globules. So that's how when milk has been homogenized, it's done by shaking the milk and cream. Another way you could think of it is if you fill a bath with the old-fashioned taps. I apologize, I have to go back to ancient technology, where you have a hot tap and a cold tap, and that was seen as a very sensible arrangement. You turn on the hot and you turn on the cold, and you're trying to get the bath water just right. So what you do is you kind of stirring around the water with your hand to try and even out the temperature of the water. And that's exactly what the physicists were kind of concerned about when they looked at this map of the radiation of the universe. They were sure that the early universe, i.e. when it's after Big Bang, must have had wide variations of energy and temperature, and there was reasons for that. So it would have had its hot and cold areas. And something must have happened to smooth out the temperature. And it must have happened by the time of this cosmic microwave background, this point of 380,000 years after Big Bang. Now, the problem was, when you look at it as it is now, how do you homogenize the temperature across the universe if different areas can never have been in contact with one another, And I want you to just look at this picture. This is the same map, and I put an orange dot for us right in the center of the universe. And if we look out in one direction towards A, we can see back, say, 10 billion light years, right? And then we look in the opposite direction, we can see B, which is 10 billion light years away. So that's a total of 20 billion light years. A and B are apart by 20 billion light years. Now, because of Einstein's restrictions on the speed of light, there isn't time in the universe, or in the life of the universe so far, for radiation from A to mix with B. And this is called the horizon problem. That the mixing could only have happened amongst areas according to what they had time to for radiation to travel from them to this other point and back. But the universe is pretty well isotropic, the same properties in all directions. So where did we get this uniformity of temperatures for everywhere on our map? Now, the situation is considered that it's not a coincidence, and the cosmologists conjectured it has to happen before 380,000 years. So how do you deal with that? What was able to mix the temperatures of the universe, mix it all up and smooth it all out, in the picture of the standard Big Bang expanding universe? And the solution that's proposed is called inflation. And this was the brainchild of Alan Guth, working at Princeton and Cornell. His idea was that a huge inflation of the universe might have taken place in the first minuscule fraction of a second of the universe. It's a different, inflation is different from the general expansion of the universe, the long-term one that we've been talking about. The inflation is just something that happens in a fraction of a moment without hardly any time happening at all. And it was proposed by Guth to deal with another problem, which I'm going to take you through, called the flatness problem. And the flatness problem is why the actual value for the density of matter in the universe so closely matches the value of the critical density that is needed for the universe to exist. Let me explain that for you. Now, density is the amount of matter in a particular volume of space. So density equals mass over volume. Relativity theory proposes that the amount of matter in any space has an impact on the curvature of neighboring spacetime. So you've seen this type of picture of the grid and the balls and planets kind of warping space in this way. This is Einstein's model of how mass warps spacetime, and it accounts for how gravity works. But so instead of thinking of gravity as a force, we think of gravity as linked to the geometry of spacetime. Now, the issue that Guth was working on is how the emerging spacetime of the universe might be differently affected by the different levels of density of all the matter within it. And I'll explain how that worked. You see, there is only one value for the density of the universe that is just right for galaxies, stars, and planets to form. And this particular value is called the critical density of the universe. It's the one that produces what is called a flat universe. That doesn't mean that the universe is flat in a two-dimensional state. It's how it's been modeled in terms of space-time geometry. Now, you see the drawing here. It's got the flat universe up at the top, and it uses a coefficient called omega. Omega is the actual density of what's out there in the universe divided by the critical density. So the thing is that you need the actual density to equal the critical density in order to get a flat universe. So if the actual density value is the same as the critical density, then omega will equal 1. So the figure 1 is what gets you a flat universe. All right? Now, what happens if it's not 1? Well, if it's bigger than 1, i.e. there's too much matter in the universe for its volume, omega is greater than 1, and that means the density is greater than the critical, and that means weird things start to happen to space-time. There's too much matter, it's twisting and curving space-time too much, it warps, it folds in itself and produces what's called a closed universe, and sometimes referred to as the big crunch, i.e. if this was the situation, if the density was more than the critical level, then the universe would have collapsed in on itself before it had got off the ground. It's not a question of doing this later, it's a question of it would have happened yonks ago. Or, if the density is below a certain amount, i.e. that there's too little matter in the volume of the universe, then the universe would run away with itself and expand too quickly, with all its mass and matter becoming ever more sparse and colder. This would be an open universe, heading towards what is called the Big Chill. And that situation would also mean that the universe would not have formed. No planets, no solar system, no gas, nothing would have formed. It would just be kind of gases out there. There is only one value for the density of the universe that produces a flat universe, And that is why it's called the flatness problem. Now you might say, well, why is it a problem if it ensures that the universe exists and there's planets and it's looking after us? But as we explained, omega is the ratio of actual density of the universe to the critical density. And for our universe to be flat and to exist, omega must be 1. And you might ask, well, how close to 1 does it have to be? Is 2 or 3 okay? Is 1.5 okay? Nah. It has to be within 60 decimal points. If you vary the 60th decimal place, the one in red, by just 1, you've destroyed the universe. This is an uncanny degree of fine-tuning of what is called a free parameter of the cosmos. A free parameter is a value that is not predicted by a theory. It is what it is without any known causality. Basically, it just happens to be this value by chance, coincidence, whatever you want to call it. That's why flatness is a problem. It's great for us here on Earth because it provides the universe that we enjoy. But it provides a headache for cosmologists because they've got to explain why something that has the value of the density of the mass of the universe, a value that could be entirely arbitrary, has a value that precisely matches the only value that will give rise to an inhabitable universe, a place for life and consciousness. Now, that was the problem that Alan Guth wanted to address and why he proposed inflation as a solution. This is what inflation looks like. He proposed that there is a period of rapid, unimaginable increase in the size of the universe, or at least in the scale of the universe from what it was within a fraction of a second. So let me take you through this diagram. The start is showing as the glowing point down the bottom left-hand corner. It's artistic, there is no glow. The dotted red lines are the arrow of time coming out from that start to the end of the period of inflation. And the increased size of the universe at the end of inflation is shown by the orange circle. Now, you may be shocked at the actual size at that point. It was 1 centimeter. The universe was 1 centimeter wide at this point. But it was unimaginably small before then. And all of this happens within a tiny fraction of the first second of time. And then after the inflation period, the universe settles into a kind of steady-ish continual expansion shown by the blue timelines going from the inflation period out to today. Now looking at this more closely, we've got along the x-axis we have time, and then we have the radius of the universe going up. Both of these use a logarithmic scale. Sometimes that can be confusing. So I've shown where 1 second after the start of the Big Bang is with the vertical dashed blue line. So the inflationary action is all happening, it said, around the point of 10 to the minus 35 of a fifth of a second. So 35 digits, 35 decimal points and a 1. That's the amount of a second it's happening. And it's happening pretty well. As soon as it starts, it stops or slams on the brakes and comes to almost a halt. But then it settles into a speed of expansion that is a very precise rate. And it's the rate that gives you the density that is equal to the density of the critical density that we need for a universe. Now, this is quite incredible that the inflation produces an increase in the scale of the universe of 20 to 50 orders. That's 10 to the 50 orders of magnitude. Estimates vary. In what amounts to no time at all. And then it grinds to a comparative snail pace at such a precise rate that is absolutely perfect for producing a flat, i.e. space-time flat universe. Now, Guth's inflationary universe was adopted because it corrected an issue with the predictions of the existing Big Bang theory. And basically, inflationary universe and Big Bang universe became merged to form the basis of the present-day standard model. But it's not without its detractors, modern detractors, raising the same questions about information and causality that we've been asking. The sort of questions that, well, what force or what initiates inflation? What's the circumstances? Where does it come from? What are the circumstances? Why was it like that? And why did it happen then? Now, there are some ideas and some suggestions to address these ideas, but are considered incomplete and speculative and problematic. A harder set of questions for physicists to explain is what stops it and why it stops when it does. Because the models indicate that once inflation starts, it basically should spiral out of control. And physicists are struggling to find a plausible mechanism that would slow it down. And although inflation is meant to address the flatness problem, actually it raises another big question. How is that inflation that you've just proposed able to slow down to exactly the degree of expansion that fulfills the critical density? Now, if you can't explain what stops or slows inflation, then you really haven't got an explanation of why it stops to such a precise rate of expansion, producing the perfect density for what the universe is about to do. And this troubles cosmologists because it indicates that the universe seems to know where it's going and what it's trying to do. How can the laws of physics know in advance what it is intended to produce? Fred Hoyle posed it in this way. He said, and this is a quote, "The universe has to know in advance what it is going to be before it knows how to start itself. For instance, at the time of 10 to the minus 43 seconds, the universe has to know how many types of neutrino there are going to be at 1 second, so that in order that it starts off expanding at the right rate to fit the eventual number of neutrino types." So now we have two related major fine-tuning issues. We've got the matching of the critical density, which is not explained, and we've got the process that initiates and ends inflation, leaving us with the perfect critical density, also not explained. So where and what is this information that is coordinating this process? Inflation is just one of the many examples of an information issue that the standard model must contend with, and we're going to explore many more. Is this simply a chance coincidence, or should we be looking for a source of information and coordination? Now, this flatness value of omega, these fine-tuning issues are just one of many parameters that currently persist within cosmology and physics. And the physicists really don't know how many of these free parameters there are. And I'm just going to repeat the point I made a little earlier, but in a little more detail. Cosmological free parameters are specific numbers of ratios and values of properties, or ratios of the values from one object to another. And these numbers, these parameters, cannot be generated or predicted from theory, i.e. you can't say because this is like this and this is like this, therefore that number, that thing will have that value. No. These are actual values contained within the properties of matter that seem to have just been inherent. Although the theory cannot predict why matter has these values, because the actual values should be arbitrary and not related to having caused, what we find is these arbitrary values are crucially precise to be exactly what they need to be for the universe to exist. Now, mathematicians, of course, wonder if there must be some connection between these numbers, but at present, we cannot find such connections. We cannot predict or produce the value of these numbers from the values and properties of anything else that we know of. That's why they're called free parameters. They're sort of primeval values. They are what they are. Why? Because that's what they are. There seems to be no way of explaining why they should have the value they have. It's just the way it is. So, these parameters are not generated from theory. They should be arbitrary. And the question is, how is it that they come to be so precisely specific? Now, some scientists, being troubled by this, hope that a quantum explanation of gravity, once that's developed, there may be a way to explain some of these relationships between the various forces and particles. Or there may be some other laws that determine how to make a universe. Or there may be some other exotic, so-called naturalistic ideas that there is some extra universe, i.e. aliens outside of the universe who are building their own universe, and maybe we'll get to do the same. Or there is a quantum superposition of all possibilities for the states of the universe, and this one is just the one that got it right. Or another one, which we're going to look at in a bit more detail next week, the idea of the multiverse, the idea that there are an infinity number of universes popping out of nothing again and again outside of time, and we just happen to be in one that got it right. We'll look at that a little bit more next week. But the fact that we require all these kind of rather speculative, untestable notions about how fine-tuning might occur, and I'm not sure I've even defined fine-tuning. Fine-tuning is that concept that the universe contains these parameters, these values, these constants, these principles that are so precisely tuned, as you would the string of an instrument, so precisely tuned in order to produce the result of an effective universe. That's what fine-tuning is trying to deal with. But the fact that the cosmologists are trying to kind of come up with all these ideas tells us the point that we are trying to make, that there's a lot of specific information in the narrative of the development of the universe, information that demands to be accounted for. Now, quite reasonably in physics, there's a philosophical bias against free parameters, because the scientific method is intended to explain the values of properties by reference to how they have been caused or produced from something else. So, but free parameters don't fit into that neat requirement. They indicate that there are values and properties of matter that you have to accept as fundamental, as axioms, as premises, values that are set as the starting points for matter and for building the universe. And when those values turn out to be so precisely tuned that if they had any other value varied by even a smidgen, the universe couldn't happen. If that's what you find, then it isn't satisfactory to simply suggest this is all one big coincidence. Thinking of parameters as coincidence is not the spirit of scientific inquiry. We must look deeper for causality. Now, the Atma Paradigm understands the nature of matter in this way, that these values represent the specific information content that permeates the components of matter. They define the properties of particles and the forces that act on them. And the one source of specifying information that physics has not explored in relation to the plethora of free parameters, the one thing it hasn't explored in this context is consciousness. So, I'd like you to take away from today that we surely live in a universe of information. There is precise universe in the starting conditions of the universe. There is additional new information in each of the components of matter as they come to be, and in each of the fundamental forces that appear at the start of the universe. It's finely tuned, and there is new free information that has not been shown to be this is all new free information, not being shown to be the product of values of anything that came before it. And there's also information coordinating space and time, and information coordinating the structure of galaxies, stars, and planets. We've approached the phenomena of a universe full of information, and I've tried to start that discussion by telling you part of the story of the development and the history of the standard model. And I did that so that we can understand many of these key aspects of the model and the rationale behind them. So that's given us a glimpse of the issues that cosmology faces in accounting for our universe of information. And next week, we're going to go through other features of the standard model as it currently stands. And we're going to examine novel information where it might be appears, how it might be required, and if the standard model can adequately account for it. Now, all of this will lead to our proposition to incorporate the one source of novel information we keep mentioning. Is there a way that consciousness in some form is able to impact the information content of the universe, perhaps from its inception? Now, such an idea may seem ridiculous to the physicalist camp because they assume, from their perspective, that consciousness was not around at that time until much, much, much later. But as we've tried to point out in this series, perhaps they've got consciousness wrong. If consciousness isn't a product of matter, but an actual fundamental component of reality, like matter, energy, and information, then it may be a serious error to leave it out of the cosmological equations. So please join us next week for more about the information of the universe of information. And we'll be looking at what's at time t equal 0. What's at the start of it all. So same time, live next Thursday. That'll be the 12th of November, and at 6 p.m. UK time. And again, if you've got any questions or want to contact us, info@s-pi.org. Thank you very much indeed.